Okay, hi everybody, can you hear me? Just
yes.
to check. Okay, good.
Yes.
Yeah, thank you very much for coming. My name is Max. I am a third-year PhD student at UCL. Working on natural language processing and advanced machine learning. And I will be talking about examining what level adversarial examples for text classification today. In the next 50 minutes or so, I will be talking about adversarial examples in general first, to give a bit of a background. Then I will be talking about their sort of formation, how adversarial examples are built in natural language processing specifically. And then I will be talking about two research projects that we've been working on in this context. So to give a bit of an intro, adversarial examples result from small perturbations to input data points that lead a learning model into false reasoning. I think some of you might have heard of what adversarial examples are. They have initially been discovered in computer vision in around 2014. And here's an example of how this would look like in image classification. So on the left-hand side, we can see an image of a panda, which is correctly classified by a trained neural network with 57.7% confidence. And adversarial examples result from these small perturbations that we add in pixel space to the input image in order to obtain a new image that you can see on the right side. Interestingly, to the human observer, we don't see any difference. So these changes are humanly imperceptible. But you can see that after adding the perturbations to the input pixels, the prediction changes from panda to gibbon with 99.3% confidence. So this is what adversarial examples are in computer vision and especially image classification. And of course, this is a problem because since we as humans clearly would classify this image as a panda, and the neural networks do not, we see that there are some vulnerabilities in terms of their ability to generalize to unseen examples. A couple of examples in the real world of where adversarial examples play a role. On the left-hand side, you can see how they can be used in face recognition. So there's this paper from 2019, which proposes to 3D print adversarial glasses that, when worn by human beings, mislead face recognition systems in recognizing people different from the people that are actually wearing the glasses. So on the right-hand side, here you can see, for example, this person wearing these glasses. And when wearing these glasses, the person is misclassified as Brad Pitt. And then on the right-hand side, you can see the same, or the application of adversarial examples in speech recognition, where you can perturb audio frequency input waves to neural networks, to a neural network, then that then make the neural network misinterpret the input wave. So we have a clean input audio frequency wave, which is kind of translated into the text. It was the best of times, was the worst of times, and you add a bit of perturbation in to this audio frequency wave, and what you get out is it is a truth universally acknowledged that is singular. So here you can see two sort of applications of adversarial examples in different modalities. They exist across vision and speech recognition. So it has been shown that you can adversarially attack certain methods in reinforcement learning as well, and especially in natural language processing, which I'll be talking about today. To give a quick overview, how can we craft adversarial examples for images? So we have a problem that given a pair of an image and a label X and Y and a classifier F that correctly classifies X as Y. Then sort of an adversarial attack onto this would be about finding a perturbation eta for X to craft an X prime that is just X plus this eta that satisfies a set of certain constraints. The first one is, or desiderata. The first one is that the perturbed image should be misclassified. So the class label of the perturbed image should be different from that of the original one. And the second one is that the perturbation shouldn't be too large. So in this case, the max norm of this perturbation should not be larger than some epsilon. And this epsilon is usually sort of referred to as a perturbation norm, or you can interpret it as the sort of imperceptibility threshold that you have. A potential approach to this kind of problem, one that has been put forward quite early in 2015, is to use the objectives gradient to find a perturbation that then maximizes the model's loss. So the idea here would be to say, okay, we have access to the model's internals. we can compute the gradient of our loss function with respect to the input image. And then this gives us the direction in which we can maximize the loss as we change the input x. So the idea is here to say, okay, we kind of want to follow this direction in order to increase the loss as we change our input x. We use the sign of this, and then we multiply this by epsilon in order to make sure that we satisfy this imperceptibility constraint here. This is referred to as fast gradient sign method because it is fairly fast. You need to compute only a single backward pass through the model in order to get the gradients with respect to your inputs. And sign because you use the sign of this gradient multiplied by epsilon, and then you can perturb your input image in this direction. So this was just a quick overview of one fairly straightforward approach of how you can sort of find adversarial examples. When we deal with text, we have a bit of a problem because as compared to images, text is usually represented with a discrete set of tokens. So adversarial examples were initially discovered in images, but compared to image and audio processing system, in text we deal with a set of sort of words that form sequences, and we need to perturb those sequences in an adversarial way. So that means some of the attacks that have been proposed in the area of computer vision, they do not necessarily transfer across modalities, especially not onto text. So how do we, what do we do about this? How do we generate textual adversarial examples? One of the desired properties that I mentioned earlier of adversarial examples is that they should be imperceptible. But this is impossible to, or that the changes should be imperceptible. But this is unfortunately impossible to achieve on textual data because every manipulation to an input sequence is unavoidably perceptible to a human reader. So if you change an individual character or an individual word, or you paraphrase the entire sequence, a human reader will be able to see that there has been a change. So instead of aiming for this visual imperceptibility, what textual adversarial examples do is they aim to be semantically imperceptible. So we want to, given an input sequence, you want to find another sequence that is semantically equivalent to the original one, yet it is misclassified by a reference model. So an example for this would be here in the context of sentiment analysis. Imagine you have an input sequence that says, I really hate that movie, and you have a text classification model that correctly classifies this as negative. As an adversary, you might change individual words to generate a sequence, I totally dislike that film, which is semantically very similar to the one above, because we changed really to totally, hate to dislike, and movie to film. Yet you could imagine that this is then classified as positive by a text classification model. Hence, we would say that this is an adversarial example because this is not how it should be. It's clearly still a negative sequence and should be classified as that. Okay, so how do we achieve this kind of semantic imperceptibility? So for adversarial examples in the context of natural language processing, we have three kind of levels that we can look at. The first one is a character level, where we change individual characters of a sequence. So an example paper proposed to use visually similar character substitutions, where they have an input sequence, for example, I really like that movie, and they changed certain individual characters with visually similar ones. So we as human readers would still be able to clearly read that sequence as I really like that movie. But since the encodings of individual characters changed, the text classification models are likely not able to understand or to process these words as they're intended to be processed. And then this makes it more likely for them to be adversarially vulnerable to those examples. This is based on the assumption, on the observation that certain controlled character manipulations do not really alter sequences' meaning. So we see this above, obviously. We are still able to read this as I really like this movie. And this is kind of what this character level perturbation idea is based on. So in this paper here, you can see another example of a news classification model where we have an input sequence that is classified as the topic world with 57% confidence. And a single character change, in this case, the word mood has been perturbed to the word moop, flips the prediction label or the prediction label from world to science and tech with 95% confidence. And even that individual change doesn't really affect our ability to understand what the sequence is about. Then on word levels, the word level would be the second level at which you can perturb, adversarially perturb input sequences to text processing systems. Here we could use synonyms, for example, with available online databases such as WordNet, which provides a set of synonyms for any given word that you query against the database. Or you could use something like word embeddings. Word embeddings are vector representations of words that are learned such that they model semantic relationships between individual words in a given vector space. That means that if you have a vector corresponding to a word, you'll be able to find semantically similar words by finding nearest neighbors in that vector space. So this would be something that, as you've seen before, we could, for example, change "I really like that movie" to "I totally like that film," or "I truly like that film," or "I truly like that flick," and so on and so forth. And then the third dimension at which we could perturb textual sequences would be on a phrase level. So that means we use something like paraphrase neural networks, which has been proposed in this paper in 2018, where you say you have an input sequence, an original unperturbed input sequence that says there's no pleasure in watching a child suffer. You could generate a paraphrase that reads, "In watching a child suffer, there is no pleasure," which is clearly very similar to the original one. In this case, this is a successful adversarial example, which would be misclassified by a reference model. So this was a bit of an introduction into how adversarial examples in natural language processing look like. As I said earlier, I will be talking about two research projects that we have been working on in the last 2 years. And the first one is called frequency-guided word substitutions for detecting textual adversarial examples. This is a joint work with Pontus Stenetop, Bennett Kleinberg, and Lewis Griffin, and we presented this earlier at ESCL this year. The idea in this project is that we wanted to investigate adversarial word substitution. So we generated adversarial examples and observed that some of these attacks, they tend to replace words with less frequent substitutions. And you can see this here in this figure where we have an unperturbed original input sequence, a clever blend of fact and fiction. And then you can see two attacks here, the genetic attack and the PWWS attack, which is short for probability-weighted word saliency. And these attacks, so the genetic attack changes the word clever to the word brainy. And what we observed is that some of these adversarial substitutions, they tend to map high frequent words to rarer and then therefore less frequent words. And frequency is defined as the amount of times that a certain word occurs in the training corpus that is used to train the model for a certain task. We use a log scale here, so the numbers above those words correspond to the log word frequency of those words in the training corpus. And what you can see is that the word clever is much more frequent than the word brainy. Likewise, for the PWWS attack, we have 3 adversarial substitutions. So we change clever to cunning, blend to blending, and fiction to fabrication. And we observe as well that we have this frequency shift towards low frequent words. The good thing about this is that we can quantitatively analyze this by comparing the word frequencies of all of the replaced words, so the words that have been chosen by the attacks to be replaced, and then the corresponding adversarial substitutions. And this is what we did in this work. We did statistical testing to observe or to investigate whether we can see any significant differences here, and we did. So here are 2 histograms visualizing these frequency differences. On the left-hand side, you can see, so both of these histograms are with respect to a fine-tuned Roberta model on the IMDb movie review dataset, which is another dataset for binary sentiment analysis. So you classify a sequence into either positive or negative. And the histograms show the frequency distribution of replaced words and their corresponding substitutions. On the x-axis, you have the log word frequency, and on the y-axis, you have the corresponding frequency of those frequencies. And then you can see that the green bars with the diagonal lines, they represent the substitutions, which have a tendency to be less frequent, whereas the replaced words have a tendency to be more frequent. These are represented here in orange. In our paper, we find that this holds true for various word level attacks. And we have more details on the specific statistical testing that we did there. But this is pretty much the main observation that we made by comparing word frequencies of replaced words and their corresponding substitutions. And based on this finding, we proposed something called frequency-guided word substitutions. So we thought about using this characteristic in order to be able to detect adversarially inserted words, because we now know that low frequent words are, or the low frequency of a word is potentially indicative of an adversarial perturbation. And the idea behind the method that we proposed, that I'll talk about in a second, is that we try to detect those adversarially inserted words based on the frequency, and we replace them with more frequent semantically similar words in order to see whether this change does affect the classifier's prediction on the input sequence. So this is called frequency-guided word substitutions, short FGWS, where the idea, as I said, is that we have low frequent words that we identify in an input sequence X, which has a prediction Y, and then we replace these low frequent words with higher frequent counterparts to generate a new sequence X prime. And intuitively, what we would say is that if X is not adversarial, then we wouldn't think that the model prediction should be substantially affected by this change, because if X is already correctly classified, then changing low frequent words with more frequent words shouldn't make the classifier misclassify the sequence, because it is sort of, it has a higher familiarity with more frequent words since it has been trained on those more frequently. Whereas if X is adversarial, then we might expect the model prediction to shift towards the correct class, because now the low frequent words that are indicative of a potential adversarial perturbation have been changed with high frequent words, and these high frequent words are less likely to make the model misclassify the input sequence. So there are two questions that come up when talking about this approach. The first one is, how do we select low frequent words? For this, we use a delta parameter that serves as a low frequency threshold. So we just say, for all of the words X that we have that have the phi function here represents the frequency, that have a frequency which is lower than delta, we consider those for replacement. And then we replace each of those low frequent words with its most frequent semantically similar word. And in order to find those semantically similar words, we can again use, for example, WordNet or a pre-trained embedding space. And then the second question is, how do we measure a prediction confidence change? For this, we introduce a parameter which we call gamma, which serves as a threshold for the change in prediction confidence after generating our sequence X prime. So we say now the capital F corresponds to the prediction probability on class Y given input X. So we compute the probability of X on input, or of class Y given input X. And from this, we subtract the probability of Y given our input X prime. And if this difference exceeds this threshold gamma, then we can say, okay, X might be adversarial, because the prediction confidence on that class that it predicted initially changed drastically, which might be a clue that this sequence has been adversarially perturbed. Both delta and gamma are tuned on the validation set, just as a side note. Gamma can be used, when we use the validation set, gamma can be used in order to control for the amount of false positive that our detection mechanism generates, because we can say we compute the difference between our unperturbed input and the transformed unperturbed input on the validation set. And we can choose gamma such that only 10% of those sequences are flagged as false positives. But I'll talk about this in a second in more detail. We validated our approach with the following experiments. We looked at two sentiment data sets. The first one is the binary Stanford sentiment tree bank, and the second one is the IMDb data set, as mentioned earlier. We look at the genetic and FGWS attacks, which have been proposed recently. The target model is a fine-tuned Roberta model that has been fine-tuned on the training sets of these two respective data sets. And then we compare our method to a baseline called DISP, which is short for learning to discriminate perturbations. And DISP works in a similar way as FGWS. So the idea is to detect adversarial examples by predicting and replacing perturbed tokens. The main difference between DISP and our approach is that DISP is learning-based. So it has a learning-based approach to predicting individual tokens in an input sequence with respect to whether they have been adversarially perturbed or not. DISP operates on contextualized representations in contrast to our method as well. Okay, looking at some results. The main the main metric that we are interested in here is the accuracy of a model on the original, so the unperturbed and the adversarially perturbed sequences. So in this bar chart, what you can see so for each of the 4 configurations, so this is the 2 attack types and the 2 data sets, we generated adversarial examples for 2,000 test set sequences on IMDb and for 1,821, this is the entire test set for SST2. And then we computed the model's classification accuracy before perturbing and after perturbing, and then also after transforming those sequences using FGWS and DISP. And this is shown here in this bar plot. So on the left-hand side for each of the configuration, you have the clean accuracy of the model on the unperturbed sequences, which is 93% on IMDb and 95% on SST2. And then you can see that if we feed the model now our adversarial examples, so this is the green bar here with the vertical lines, we can see that accuracy drops to below chance for the genetic attack on IMDb, and for the PWS on IMDb, it is even lower, it's 41%. For the PWS on SST2 is at 57. So you can see that the adversarial examples considerably lower classification accuracy of the model on the input sequences. And what we're interested in is, of course, to restore this accuracy as much as possible by introducing our mechanisms. So if we compare these values between this, which is the column here in the bar in blue, and then we have the gray one, which corresponds to FGWS, we can see that both of these methods restore accuracy to a certain extent. So we can see that the accuracy, for example, on the genetic attack on IMDb has been restored from 48% to 74%. And using DISP and FGWS, we achieve a restored accuracy of 81% by just using these frequency-guided word substitutions in order to transform our sequence before we feed it into the model again. And we can see similar results here for the 3 other configurations. Also, what I touched upon earlier, for these experiments, we tuned gamma, so the prediction confidence change threshold, to allow for 10% of false positives on the validation side. Okay, next, let us look at some examples. Here's an example input sequence into the model, which says first good, then bothersome, which is correctly classified as negative with 74.5% confidence. If we use this sequence and generate an adversarial example using the genetic attack, it generates something like first good, then Gelling. And it is then correctly classified as positive with 88.7% confidence. Now we use this adversarial example, first good, then Gelling, and feed it into DISP and FGWS. And what we get out is first good, that Gelling for DISP, which does not change the prediction label back to negative. Whereas for FGWS, in this case, if we transform it back, we get first good, then annoying. So Gelling is now changed to annoying, and initially it was bothersome. And then it is classified as negative again with 91.3% confidence. And for the second example, we have a smart, sweet, and playful romantic comedy. Using the PWWS attack, we generate an adversarial example that reads a impertinent, autoreferous, and playful romantic comedy. And using DISP and FGWS, we can then again transform those sequences. In the case of FGWS here, we achieve to transform the sequence back to its original form. So impertinent is substituted with smart, and autoreferous is substituted back with sweet. So this is the clean input sequence again, which is then again classified as positive with 99.9% confidence.
Hi.
Yep.
That one doesn't quite look like an adversarial example, because impertinent, I'm not sure I'd read that as the same as smart.
Yeah, definitely. That is a good point. So this is something I'll talk about in a second, which is pretty much the second part of this talk, is that there's a lot of debate on the validity of these adversarial examples and whether some of these sentiment or some of these word substitutions actually preserve the semantics and the sentiment of the sequence.
Okay.
But yeah, it's a definitely a good remark. Next, I'll try to talk a bit about why those low frequency replacements actually happen. So what is kind of the intuitive idea of why we have those low frequency mappings? yeah, intuitively speaking, we can say that more frequent words are more likely to be selected for replacement just because they are, by definition, more frequent. So we have more of those in sequences, which means they are more likely to be replaced by certain attack algorithms. And then a high frequent word is unlikely to have many high frequent synonyms in a given synonym space, because if there were many higher frequent synonyms, then it is more likely that we would have chosen those high frequent synonyms instead of the word that we have chosen. So as an experiment, what we did in order to quantify this a little bit is we said, let's consider all of the replaceable words in the test set sequences. Replaceable here means all of the words that are potentially replaceable by each of the attack that we look at. And then we use all of these replaceable words and we compare the mean frequencies of those replaceable words with the mean frequency of each word's synonyms. So for each replaceable word, we take all of the synonyms and compute the mean frequency of those. And we, as an upper bound, we can also use the maximum frequency of each word's synonyms. And then we can just see how these frequency values differ to see whether we would potentially be able to replace words with more frequent words, given the synonym corpora that we have at hand. So here we can see a comparison of those using box plots. We have on the y-axis, we have the log frequency of the words again, and then you can see the distribution of frequencies for all of these three configurations. So we have the distribution of replaceable words, then that of the mean of each word's synonyms, and then the maximum of each word's synonyms. And we can see that even if we were to replace each word with its most frequent synonym, we would likely be ending up with replacements that sort of do not preserve the frequency of the replaced words. And if we take the mean, then this is even lower. This generalizes across configurations here again. So this would be FGWS on the other data set in IMDb, where we also see that difference, that we have the distribution of replaceable words, and then the one of the mean synonyms, as well as the maximum synonyms. And we have this similar picture here for the genetic attack on SC2 and the genetic attack on IMDb as well. So this gives kind of an intuition on explanation of why these low frequency replacements exist. What we did then is we tried to restrict the attacks to only allow for equi-frequency replacements, just to see how this would work out, because in theory, this would be sort of a way of circumventing our method FGWS. So what we did here is we did an experiment where we say we imposed a certain frequency constraint to allow only equi-frequency substitutions, which means that for each of the replaceable words x, the frequency phi of its replacement x prime has to satisfy this inequality, which is that the frequency of the replacement has to be larger or equal than 1 minus epsilon times the frequency of our original word. So if epsilon is equal to 0, then we have that the replacement frequency has to be strictly larger or equal. And then as we increase epsilon, we'll only look at a fraction of these. So we did this with different configurations of epsilon, and then we sort of plotted the after tag accuracy, which is indicative of the degree of success of the adversarial attack on those sequences. So if we do this for PWWS on SST2, we can see the following here. We have on the y-axis the model accuracy on the perturbed sequences, and on the x-axis we have the value for 1 minus epsilon. So if 1 minus epsilon is 0, then that means, if we go back here, that means that the frequency only has to be larger or equal than 0. So this just degrades to the normal attack as we have seen before. And as we increase 1 minus epsilon, the after attack accuracy goes up, which means that the attacks become less successful. Why is this the case? This is the case because as we sort of impose this constraint, there are just fewer synonyms for each of those replaceable words that the attack can use in order to find adversarial examples. So there's a nice relationship between the accuracy and what we see on the right here. On the right, we can see the mean number of synonyms available for each replaceable words as a function of 1 minus epsilon. And then this is there's perfectly clear relationship between how the accuracy goes up again and how the mean number of synonyms goes down as we increase 1 minus epsilon. We see something similar for PWWS on IMDb here as well. And then these are the results for the genetic attack, which are also similar to what we have seen before. So given these results, we thought about what does this mean? Does this mean that equi-frequency attacks are generally ineffective? I guess what we can say from those observations is that for current synonym corpora that we use for the attacks, such as WordNet or counterfeited word embeddings, these are limited in a way that they only have, of course, a limited set of synonyms for each replaceable word. So we thought about what we could do in order to further investigate this, and we said that the gold standard for kind of finding these perturbations or finding these synonyms that might be very effective as adversarial input perturbations could be found by humans. So we were interested in how would humans approach this task. And this leads me to the second project that I'll be talking about today, which has the title Contrasting Human and Machine-Generated Word-Level Adversarial Examples for Text Classification. Joint work with Max Bartolo, Pontus Senetorp, Bennett Kleinbeck, and Lewis Griffin, which we will present at EMLP later this year.
Can I ask a quick question first?
Of course, yeah.
So if you're replacing a high frequency word, then most of its synonyms are lower frequency. So did you compare, like, okay, is the adversarial attack more likely to replace a word with a less frequent word than a by chance substitution of synonyms?
No, we didn't quantify this.
Because it could be the case that they get replaced with less frequency words just by chance, right?
I mean, it depends a bit on the availability of. So if all of the words, all of the synonyms have low frequency, then there's no other way than replacing them with low frequency words. And this is pretty much what we wanted to show in these box plots, that the frequency of the synonyms is generally lower. So this is pretty much unavoidable that you have this frequency shift as you replace words.
Yes, but could that be because that's actually a successful strategy, or could it just be that, well, whatever strategy you use, you're probably going to end up replacing with less frequent words because there's more of those?
Yeah, so I would say yes, because the only way of replacing is using these corpora, and these corpora have synonyms that are lower frequent than the words that you choose. Okay. What do we mean if we replace words at random from the sequence?
I suppose, I mean, if you pick words at random, you're most likely going to hit upon the more frequent words.
Yeah.
And then if you replace that with a random other synonym, it's more likely to be less frequent. And so even if you're not doing it adversarially, you're going to end up replacing with less frequent words. So I'm not sure I follow that. You've explained how the adversarial attack actually works by pointing to the lower frequency substitutions.
Yeah, so we did some, no, I understand what you mean. We did some experiments in this. They are in a paper where we use a random attack, and the random attack just chooses words at random from the input, and is not guided by any more sophisticated heuristics as some of the attacks are. So it just randomly chooses words and replaces them with random synonyms, and we can see something similar in terms of frequency difference between the replaced word and the corresponding substitution.
Okay, and is that, presumably that's less successful at creating adversarial examples?
Exactly, it's much less successful, but you still see the frequency difference.
Okay, nice, thank you.
Okay, so in this project, we the backstory of this project is based on a paper from 2020, which questions the validity of adversarial examples. And what does this mean? So they argue that the existing attacks do not really satisfy certain desiderata that word-level adversarial examples should have. And these 4 constraints are defined by the authors as they should be semantics preserving. So the semantics shouldn't be changed after introducing word-level perturbations. The adversarial examples should remain grammatically correct. They should be visually overlapping, which means that the edit distance between the unperturbed sequence and the corresponding adversarial examples should be low. And then they introduce this idea of non-suspicion. So this means that an adversarially perturbed input sequence shouldn't raise any suspicion when read by a human being. Here are examples of how these constraints can be violated. So a clean, unperturbed input sequence here in this case is, shall I compare thee to a summer's day? And if you change summers to winters, so this is in this row here, this is the violation of the semantics constraint, because we see that the adversarial example has a different meaning from the clean input sequence. If we change compare to compares, then this is a violation of grammaticality. If we change many characters individually, for example, we change we flip the L with a 1, or we change the S with a 5, or the E with a 3, and so on and so forth, then the original input and the adversarial example have a large edit distance, which is, according to the authors, a constraint as well that has been violated. And then non-suspicion would be where we, for example, change shall I compare thee to a summer's day, change it to am I going to compare thee to a summer's day? Because now this would be unusual to have been written by Shakespeare, and a human reader might say, okay, this sounds suspicious. One of the questions that the authors ask as well is whether these adversarial attacks are validated. The answer to this is generally yes. So an example would be here by this paper, which introduced the genetic attack that I talked about earlier, where it is written that participants were asked to judge the similarity of each pair on a scale from 1, very similar, to 4, very different. The average rating is 2.23, plus minus 0.25, which shows the perceived difference is also small. The response by this paper was then, however, studies often simply ask users to simply rate the similarity of X and X adversarial. We believe this phrasing does not generate an accurate measure of semantic preservation, as users may consider two sentences with different semantics similar if they only differ by a few words. So I guess the point that the authors make here is that they say, if you have a clean input sequence and you have a corresponding adversarial example, when 90% of the words are the same and 10% are different, but these 10% completely mess up the meaning, then many participants would still rate these as semantically similar, because 90% of the sequence is still the same as with respect to the original one. What is then done in this work is that they use certain methods to enforce those constraints, to make the attacks conforming more to those constraints. And as a result, the attacks became less successful. This raises the question of whether such adversarial examples can actually be found efficiently. And this is what we were interested in this work. So the question we asked ourselves is, are humans able to generate word-level adversarial examples whilst adhering to these imposed constraints? There's two possible answers to this question. The first one is yes. And then we could say, okay, current algorithms can be improved because we can see that humans can do it effectively whilst adhering to the constraints, whereas algorithms cannot. And if the answer to this is no, then we could ask ourselves whether these valid word-level adversarial examples are actually truly feasible. As a note, there has been some existing work on human-in-the-loop adversarial approaches to natural language processing, but most of those approaches, they focus on generation rather than modification, which means that they ask human participants to find any adversarial example that flips or that a model misclassifies, rather than be given an existing input sequence and then having to modify the sequence with respect to a certain set of constraints. So what we did in this work, we asked a set of human participants on an online crowdsourcing platform to perturb input sequences to a sentiment analysis text classification model. And we specifically asked humans to imitate word-level attacks. So they were given an input sequence and they were allowed to change individual words with other words. And they had to do this whilst adhering to these constraints of preserving the sentiment and the naturalness of the sequence. So participants are shown the existing test set sequences and then they replace individual words. You can see this in this image here. The color highlighting of the individual words corresponds to their word saliency. The word saliency is a proxy for the importance of each of those words for the prediction of the model. So this is a sequence which is classified as negative, correctly classified as negative. And you can see that dreadful, for example, is highlighted more than other words, which means that dreadful is something potentially indicative for the model to predict a negative class. And then we see the same thing for not worthy as well. And then the humans were asked to, sort of by double clicking on these individual words, to replace them with synonyms whilst trying to get the model to misclassify the sequence. So they had an initial prediction progress bar here, and then they had one for the current prediction, and they had to submit individual iterations of word level changes until they managed to flip the class to positive from negative, or vice versa. The interface then, of course, provides live feedback on each of those prediction changes. And we asked human participants to conduct at least 15 iterations of word level changes before they could continue to the next sequence. So the data collection in total is divided into 2 phases. In the first one, we asked crowd workers to generate word level adversarial examples, as I've shown it before. And in the second one, we ask an independent set of crowd workers to judge those adversarial examples based on the sentiment and the naturalness. And this is sort of the validation phase in which we try to find out whether the adversarial examples generated by human beings actually satisfy the constraints that we asked them to take into consideration. So on the details in phase 1, we collect data from 43 participants. The reference model is, again, a Roberta model fine-tuned on the IMDb training set. And each participant perturbs 4 test set sequences from IMDb. This amounts, after exclusion, to 170 human-generated adversarial examples. What we then did is for each test set sequence, so now we have 170 pairs of unperturbed sequences and the corresponding human-generated adversarial example. We generated machine adversarial examples using 4 recently proposed word-level attacks: the genetic attack, another one which is called Textual, a third one which is called BAE, short for bird adversarial examples, and then the fourth one which is called CMIMI-PSO. And so this gives us, for each of the test set sequences, sort of 5 different adversarial examples. Sorry. And then in phase 2, we asked crowd workers to judge these unperturbed and corresponding adversarial sequences with respect to their sentiment and their naturalness. We provided ratings on a 5-point scale, which means for sentiment, this would be a rating of 1 is very negative, a rating of 5 is very positive, and for naturalness, this would be a rating of 1 is very unnatural, a rating of 5 is very natural. We collect on average 3.55 judgments per sequence, and then we take the means of those judgments per sequence as the final values. For sentiment, we said, because we need binary labels, we said, okay, an average rating above 3 is positive and 1 below 3 is negative. We ended up having 80 sequences that had a mean rating of 3.0, which we excluded from our validation. And so now that we have collected those adversarial examples, one of the first metrics that we were interested in is the attack success rate. The attack success rate is defined by the ratio of all of the label flipping adversarial examples to all of the sequences that have been adversarially perturbed. So this gives us a value from 0 to 1, and higher is better. And here in this histogram, we can see the attack success rate for the human attack, as well as the 4 automatic attacks. And we observe that humans in roughly 49% of the cases were able to flip the label after introducing their word level perturbations. This is higher than 2 of the attacks, the genetic and the BAE one, but lower than the Textual and CMIMI-PSO. So we can see that CMIMI-PSO is able to achieve a success rate of 1, which means that all of the 170 tested adversarial input sequences have been adversarially perturbed in a way that it flipped the prediction label of the model. After looking at the attack success rate, we were interested in the degree of sentiment preservation. So what we did in order to assess this is we said, now we had the ground truth label for each of the 170 sequences, and we tried to match this with the rated sentiment, which is a binarized value for either negative or positive. And if there's a match, so if the unperturbed sequence has the same label as the corresponding adversarial example, then this is good because the sentiment is preserved, and otherwise this is bad. And here we can see the fraction of matches that we have for each of those different attacks. This is divided into label flipping and unsuccessful adversarial examples. The more interesting ones are the label flipping ones because they are considered successful adversarial examples. And what we can see here, interestingly, is that whereas all of the 4 attacks achieve a match fraction of more than 80% with respect to sentiment, the human-generated ones only preserve sentiment in 58% of the cases. So this is just interesting to observe. That means that a substantial amount of adversarial examples, of label flipping adversarial examples that have been generated by humans do not actually preserve sentiment. So that also means that for any of the subsequent analysis, we can only include those sequences that have a sentiment match, because the other ones have been invalidated by this sort of experiment. So afterwards, we looked at naturalness. How do the naturalness ratings change as we introduce our adversarial perturbations? Here are 6 histograms of the distribution of naturalness for each of the different configurations. So on the top left, we have the unperturbed sequences. And interestingly, what we can see here is that they center around a naturalness of around 3, which might be a bit unexpected, because they are unperturbed natural sequences that have been authored by human beings and scraped from the internet. And other human beings rated their naturalness on a scale from 1 to 5 at an average of around 3. So this speaks a bit to the informal language that is being used for those movie reviews. If we compare the naturalness distribution of the unperturbed ones to the different attacks, we can see that just by looking at here, the distribution for humans remains fairly similar. Same for the genetic attack. For Textual, we have a tendency towards less natural ratings, and something similar for BAE. And for the CMU-PSO, we see something similar as for the other 2 attacks here. So the interesting kind of metric that that we want to look at is the difference in naturalness, because we see that naturalness ratings of the unperturbed sequences are not perfect. So what we did is for each sequence, we compute the difference in naturalness between the unperturbed sequence and the corresponding adversarial example. And if we plot those naturalness differences, we can see something like this. So this again divided into label flipping and unsuccessful adversarial examples. And for the label flipping ones, we can see that the human attack, as well as 3 of the 4 automated attacks, introduce a negative natural difference, which means that the perturbations decrease the naturalness with respect to the unperturbed sequence. Whereas for the genetic attack, we can see that, interestingly, the naturalness increased after perturbation. For the label flipping ones and for the unsuccessful ones, we can see that the naturalness difference tends to be a bit larger. And it is negative in all of those comparisons. For CMU-PSO, we don't have any unsuccessful sequences. This is why there's no green bar here in this row. We did statistical testing on this. I'm not reporting on this in this talk, but it's in the paper, and found that most difference comparisons between those attacks are statistically insignificant. So in terms of naturalness difference, we couldn't find anything statistically significant, which, given the data, leads us to conclude that there aren't any statistically significant differences between naturalness ratings with respect to those 5 attacks. Another dimension we looked at was grammaticality. So we tried to identify the amount of errors that have been introduced as a consequence of the adversarial input perturbations. And this is shown in this table here. So on the column on the left-hand side, we have the different attack methods, and then we have the number of errors here in the column next to it. And for the unperturbed sequences, so this is attack none, we have an average amount of 10.8 grammatical errors per sequence. And this increases slightly for the human attack to 11.2, and is similar for the genetic, Textual, and CMU-PSO attacks. But it is considerably larger for the BAE attack. So you can see that the BAE attack introduces more grammatical errors than some of the other attacks. And these differences are statistically significant with respect to BAE. So this is denoted by this asterisk here. And then in the rightmost column, we have the percentage of sequences where introducing adversarial perturbations increased more grammatical errors as compared to the unperturbed sequence. So how you can read this? This means for the human one, in 34.7% of the sequences, introducing adversarial perturbations increased the number of grammatical errors of the sequence. These values are fairly similar, albeit this value is fairly similar to the genetic attack. It is a bit higher for Textual, and it is much higher for BAE, and it is the lowest for CMU-PSO. Most comparisons, but most comparisons between these attacks are statistically insignificant. So we only see a statistically significant difference between BAE and the other attack algorithms. We also looked at substitution rates. The substitution rate in this context is defined as the fraction of the number of adversarially perturbed words to the number of words in a sequence. So this means that 7.5 in this table, so this is again divided into successful and unsuccessful. For the human attack, this means that 7.5% of the words have been needed to be perturbed in order to find a label flipping adversarial example. This is similar for the genetic attack, 6.9. And here you can see the values for the other attacks as well. For the unsuccessful ones, we can see that this goes up considerably for the algorithmic attacks. And this is because they tend to be greedy attack algorithms that iteratively add individual word substitutions to the sequence until they find something that misclassifies, that is misclassified by the model. And humans do not really have this because we asked humans to only submit 15 iterations. So they do not have such an exhaustive amount of word changes or substitution changes in for the unsuccessful attacks. And then finally, we looked at the number of queries needed by each of the attacks. And the number of queries refers to the number of inference steps that each attack has to make in order to find an adversarial example. Because these attacks use certain heuristics by, as I said before, by iteratively changing individual words. They try to identify how much these word changes affected prediction confidence. So for each of those tests, they need to run a query against the model in order to obtain a prediction and a corresponding confidence score. And here we can see the comparison of number of queries needed between humans and automated attacks. Again, divided between successful and unsuccessful attacks. This means here in this table, this means that for the human-made adversarial examples, humans need on average 10.9 queries against the model in order to find a label flipping adversarial example, whereas this is much higher for most of the attacks, or for all of the attacks. So genetic attack needs on average 3.5 thousand queries against the model in order to find a successful adversarial example. For Textual, this is around 515. BAE, it's 293. And then for semi-PSO, it is the largest. So the PSO attack needs on average 141,000 queries against the model in order to find a successful adversarial example. So this is quite interesting because what we see here is that humans require notably fewer model queries than automated ones. They are able to find adversarial examples in a much more efficient way. And one of the questions here is, of course, how are humans so efficient at doing this? Here's an example sequence of the data set. In the first row, we have the unperturbed sequence. It boggles the mind how big name stars such as those in this movie can be part of one of the dullest movies I've ever seen. Prediction is negative. The mean naturalness rating here is 4.5 and the mean sentiment rating is 1.9, which is good because it is a negative sequence and the sentiment match is there. The human participant perturbed the sequence by changing boggles to a Mozes and dullest to simplest, which as a result changes the prediction to positive, whilst keeping the naturalness high. So naturalness is 4.3 now instead of 4.5, and the sentiment is on average lower than it was for the original one, which is also good because we can now consider this a valid adversarial example. And then here you can see some of the changes that the algorithms did. So Textual, for example, only changed dullest to neatest, and semi-PSO changes dullest to deepest. So to conclude the findings in our second project, we have seen that automated attacks preserve actual sentiment better than human ones. Human automated attacks are similar in terms of their natural differences, so we didn't find anything statistically significantly different here. This also holds true for the grammaticality. However, humans need only a fraction of the number of model queries required by the attacks as compared to the automated ones. And this is something which is quite interesting. So in future work, we are first of all interested in how these differences are for more formal text, because we have seen for the movie reviews, we had naturalness ratings which weren't optimal. They were centered around 3, whereas you would expect something human authored to be higher. So it would be interesting to see how those differences look like if we look at more formal texts, such as journalistic or academic writing. Then we are interested in which strategies humans follow. Is there anything, are there any patterns that we can extract from the data that we have based on our humans' approach to this task? And if so, can we use some of those patterns to build better automated attacks that ideally remain as effective as they are right now, but only need a fraction of the number of queries as compared to what they need now? And finally, we'll be interested in how do humans do when these constraints are relaxed. So if they are not restricted to only make word level perturbations, but can do phrase-based perturbations, how do these differences between human and machine generated adversarial examples change? And with this, I am done. And thank you for your attention, and happy to open the floor for any questions that you might have.
If there are no questions, then I will stop the recording now. Thank you very much for participating, and thank you very much for the very interesting talk, Maximilian. If there are questions later on that you think of, then obviously do feel free to reach out to Maximilian or send questions via me, and I'm happy to pass them on. So thank you very much for attending, and thank you for your talk.
Thank you, everybody.
Thank you.